the many questions that have not been asked yet, so we can just go ahead and ask some within the break. Thanks very much.
Okay. I would like to introduce our next speaker. I mean, Sami has set the standard, so we can expect much more today. So the next speaker is Daha from Leiden University in the Netherlands. If you look for his CV, you'll read he graduated in 1973, so more has been around in the field for 45 years. And if I ask myself where I was in 1973, I was in second grade. And he has devoted most of his life to complement, and that's what he's going to talk about now. No, thank you.
So thank you very, very much. In the first place, I thank the organizer for inviting me here. For me, it has been great to listen to the first talk because it was extremely interesting that you have these many developments in this field of nephrology. But today I've been asked to talk about complement involvement in global nephritis. Actually, complement is everywhere. So in the first place, complement plays a role in almost every type of renal disease. I've given a few examples here on this slide, but you can add anything to it. Because when I teach the students, I tell them one thing. Your endothelium is clean on the day that you're born. And from that day on, everything you eat, are exposed to, etc., determines the integrity of your endothelium. And that endothelium, once it changes, is recognized by your innate immune system as foreign. And from that moment on, potentially, not only complement, but other innate immune factors start to play a role. So if you go through a number of, let's say, examples, we can see, for instance, C1q deposition in patients with SLE, complement activation in IgA nephropathy, and membranous nephropathy. This has been a very exciting story, and you have followed it obviously. And this is an autoimmune disease now, and especially IgG4 is involved. We still do not understand how this IgG4 actually supports complement activation and generation of the C5-PLC9 complex. And the same may be true also for the fibrillary GN, as we have heard just a minute ago. And these are the developments in the most recent period, say during the last 10, 15 years, about the histological findings in C3G, which include MPGN, C3G, dense deposit disease, etc. And it has been shown that here, deregulation of complement is the main factor which determines that complement activation takes place. When we talk about complement activation, we have to distinguish two things. One, activation of complement in the fluid phase, say in the circulation. And second, the consequences of complement activation. So once complement activation takes place, activated C3, as I will show you in a minute, can bind covalently to neighboring tissue and cells and support further complement activation. At the same time, local in situ complement activation can occur because of the antigen which is deposited there, or by the interaction of an autoantibody with a local antigen, or by deposition of circulating immune complexes. Once these complexes deposit in tissue, that can lead to complement activation and direct injury to the tissue. It is inferred that the activation of complement at the tissue level, once it occurs there, is much more efficient to cause injury than circulating complement, which is activated somewhere in the neighborhood of that complement attack. So in C3GN, most of the complement activation is taking place in the circulation, or in a few cases, because there's deregulation of complement activation at the cellular level. So what is a complement? Let me see whether this thing works. So complement is only a little part of our immune system. As we know, there's innate immunity and acquired immunity. The day that you're born, you're mostly dependent on innate immunity, except the antibodies which you have actually acquired during birth. And during the first 16 months of your life, you're much more dependent on innate immunity than acquired immunity. In innate immunity, complement not only, but a number of other soluble mediators play a role together with cellular components to defend yourself and protect you. Once you have overcome this, the antigens to which you are exposed are presented via these molecules to antigen-presenting cells, leading to activation of T and B cells, production of antibodies and cytokines, which then give you the full support of protection. It has been shown in this model that complement is essential. For instance, if you take rats, deplete them of complement, immunize them with foreign antigen, then they are not able to sufficiently react with a good antibody response. So complement alone is very important for the presentation of antigen and induction of acquired immunity. And that has not been shown only in animals, but also recently confirmed from many deficiencies in complement found by in humans. So what is complement? In the first place, the complement has many biological functions. A few of them are, let's say, direct pathogen elimination, such as bacteria, viruses, etc. It is involved directly in the induction of phagocytosis via opsonization. It's very important in the induction of inflammation and in chemotaxis. Furthermore, it's very important as an interface between innate and adaptive immunity. It links innate and acquired immunity. And it's very important for the clearance of immune complexes. And this is a very important function, as I will show you also in a minute. So what is complement? Don't look too much in detail to this picture. You can all read it in this review by Felix Populaars from the University of Groningen. What it brings together is there are three pathways of complement activation at the moment. The classical pathway, the lectin pathway, and the alternative pathway. Each of these pathways can be activated by specific soluble pattern-like recognition molecules. And each of them has a number of serine proteases which lead to further activation, and most important is the activation of C3, which then subsequently leads to activation of C3 and C549. You see in the boxes that there are a number of proteins indicated here. These are, for instance, C1 inhibitor. These are so-called inhibitors of complement, which control the degree of complement activation. So if you don't have these activators, then you may be in trouble. Next to fluid phase inhibitors of complement, like C1 inhibitor, factor I, and factor H, there are a number of cell-bound, tissue-bound inhibitors which protect you against activation of your complement in such a way that the cells and tissues are not damaged. So this is the main message which you have in the complement field. So what is the most important thing? The most important thing is that complement, let's say proenzyme C3, is activated to a large fragment and a small fragment. This activation occurs by these two or three pathways which lead to generation of convertases, C3-cleaving enzymes, which are complexes of C4 and C2 activated, or the amplification convertase activates C3 and factor B. These two enzymes determine how much C3 will be activated. When C3 is activated, a very labile thioester is exposed, and this labile thioester is essential for the covalent binding of this C3b to the activator. So let's say 1,000 molecules of C3 are activated. Because there is so much water around, only a few of these activated molecules will be attached to your tissue. or to deactivate it. And then that then determines further activation of complement. So you have to remember that there are two convertases, and these convert C3 from pro-enzymatic form to an activated form, where this large fragment can attach itself to cells, to immune complexes, etc., etc. And then there's small fragments which are C3a, which are phlogistic, which can activate endothelial cells, etc., etc. So once you have a few molecules of C3b deposited on the activator, you need a kind of amplification to allow the deposition of large numbers of C3b on the surface of your activator. This amplification is dependent on C3 itself, factor B, properdin, and factor D. The latter I will come back to you again because there's a new development in this field. So once you have deposited C3b on the surface of the activator, this allows now for the first time interaction of your pathogen via C3b with specific receptors. And the first set of receptors is CR1. These receptors, C3b receptors, are found mainly on erythrocytes and on follicular B cells and dendritic cells. In plasma, there are two inactivators, factor I and factor H, which convert this factor C3b to so-called IC3b, meaning that it's not more able to activate C5 and C9. But it uncovers a very important function, namely the interaction with CR3, the phagocytic C3 receptor. And these are found mainly on PMNs, macrophages, etc. And they are very important for the ingestion and elimination of, let's say, bacteria, viruses, etc. So this is probably one of the most important functions in the complement field. A further degradation, which occurs by plasmid-like enzymes, converts this molecule to so-called C3bG, a small fragment, and this then interacts specifically with CR2. These receptors are found mainly on follicular B cells and on dendritic cells. And they are very important for the presentation of the foreign antigen to your own acquired immune system via dendritic cells, etc. So this is probably a very interesting phase in the development and, let's say, generation and activation of acquired immunity. So in humans, C3b receptor is very important for the clearance of immune complexes. Every day when you have breakfast, lunch, or dinner, you eat a lot of foreign antigens. And you have, in general, made antibodies against these antigens. So every time you have a meal, you generate a lot of immune complexes. And still, potentially, these immune complexes can deposit it at random in tissue walls and cause inflammation. But that doesn't happen because these immune complexes activate complement immediately, acquire C3b on the surface, and these complexes are then interact with phagocytic cells in the liver. These phagocytic cells get activated, they secrete proteolytic enzymes which convert this C3b to IC3b. At that moment, the interaction, the affinity for the receptor goes down, the immune complex is ingested by the liver, and the erythrocytes go back into circulation. If you don't have complement, immune complexes are eliminated, of course, by Fc receptor-mediated mechanisms, but they can also deposit at random in tissue walls. So, by attaching these immune complexes to the erythrocytes, you keep the immune complexes away from an endothelium. So you can now imagine if you don't have C3 or you're not able to activate complement, then these immune complexes are free, they stay close to the endothelium, and they can cause injury. Let me move to the terminal complement pathway, C5 till C9. So once you have generated sufficient C3b on your activator, the terminal complement pathway or membrane attack complex can be generated. This complex can insert itself in biomembranes And you can imagine if this is the inside of the cell, it can leak out and lead to cell death. In the past, we were thinking that cytolysis was the main function of C529. What we know now is that small amounts of C529 lead to cell activation, upregulation of production of chemokines, oxygen replicas, and T-cell molecules, potentially increasing your potential of innate immunity to a higher level. We know that innate immunity is almost constant, but during inflammation, it can gain some additional function. In contrast to, for instance, acquired immunity, immunoglobulins, etc., which can amplify themselves many fold. Intermediate amounts of C529 lead to apoptosis and silent elimination. On a daily basis, billions of cells in our body undergo apoptosis. And this is simply to keep your tissues clean, etc. In the very past, we were believing that, for instance, brain cells were generated once, they stayed there, and nothing happened. These days, we know that every organ in the body is renewed all the time. And it's very important to know that complement is very essential in this process as well. For instance, if you take a liver from a rat, cut off a piece, and that liver piece will just grow again. But if you deplete the animal of complement, then the growth of the liver will not take place. So there it has been shown that a fragment of C5 is very essential for this, let's say, increased homeostasis of your own tissue. Very large amounts of C529 lead to cell lysis, and that is associated with inflammation. So if you, in pathology, if you see C529, it's very important to know how much C529 there is there, because it can be beneficial to the host, but it can be also detrimental to the host. So this is a balance which we have to try to understand. I would like to move to the new developments in the complement field. And there, I see that I made a mistake. There are 3 serine proteases in the lectin pathway. So I mentioned to you there were 3 pathways for complement activation: the classical, the lectin, and the alternative pathway. The question at the moment is, do these 3 pathways really exist in separate dimensions? And it seems that the most important pathway is the lectin pathway of complement. There, activation takes place by recognition of, say, an antigen via menin-binding lectin, phycolins, or collectins. They are associated with 3 main proteins: menin-associated serum protease 1, 2, and 3. And each of them have a specific function, and this has been elucidated recently. So you see that MASP1 is a very important serine protein. In the first place, is directly responsible for the activation of MASP2 and MASP3. And indirectly, via these molecules, it can activate C4 and C2. Additionally, MASP1 is involved in PAR activation, calendulin, thrombin activity, etc., linking this pathway and complement to, let's say, protein and other ways. And also, what is very important, that MASP1 can be inhibited by C1 inhibitor. And this is important because you have to be able to inhibit it. So in cases of inhibition and lack of inhibition, you have a problem because the MASP2 is a very versatile activator once it's activated by one of these 3 lectin binding molecules. So I mentioned that MASP1 is very important for the activation of MASP2, and MASP2 is important for the activation of C4 and C2, leading to further activation of complement 5 lectin pathway. There's a new development in the field, and that is that as active MAS3, when it's activated by MAS1, is able to convert pro-factor D to active factor D. Until 3-4 years ago, we all believed that factor D was present in the circulation and in body fluids, mostly in activated state. Until the discovery a few years ago by Kinoshita in Japan, that in mice there was no activated factor D. That led to the search in humans for active factor D and pro-factor D. And now we are able to distinguish pro-factor D from D, or for instance also in human plasma. And actually what came out from these studies is that most of the factor D in humans, in normals, is only partially activated, say 5 or 10%. The rest is present in so-called non-activated proenzyme form. We do not know at the moment, if you look at different diseases, what the ratios of pro-factor D over D are. But the D activation is very important because the amount of factor D determines how much alternative pathway of complement activation there will be. And this is very, very important because by activation of the lectin pathway, you determine directly to which extent the alternative pathway will be activated, how much amplification there will take place, etc. So this is very relevant for diseases like C3GN, atypical HUS, etc. Because it may be that the level of factor D is controlling the degree of amplification and the, let's say, the moment of, let's say, induction of disease. Because if you go through the life of many patients, early on in life, they are not really sick. But only later they have a clinical, let's say, clinical expression of disease. So the question is this balance in pro-factor D over D disturbed? So this is a very important field. So I think for in the coming years, we will have to explore in all these diseases, including the first talk, I think, how the ratio of pro-factor D over D is and to which extent it contributes to the degree of complement activation. So this brings me to this question, how should you interpret complement activating GN and other diseases? And I will just take an example, IgA nephropathy. So in IgA nephropathy, we know that there's massive deposition, central deposition of IgA, and this is mainly IgA1, and that is associated with the activation of C3. So the question is in this disease, is the lectin pathway also involved? Because we know for a long time the alternative pathway plays a role in IgA nephropathy. Here is a demonstration of the deposition of menin-binding lectins as a component of the lectin pathway in IgA nephropathy in biopsy. And this is what you see is deposition of MBL, and of course IgA is associated with deposition of MAS1 and MAS3, L-ficolin, and especially C4 and C4 binding protein, indicating that there is complement activation, presumably by the lectin pathway as well. So let's say in vitro studies, which I will not detail on, show actually that the NBL binding in IgA nephropathy is mainly limited to a large polymeric size IgA. And this is the type of IgA which we know gets deposited in the mesenteric area and leads to complement activation. So then what we did, we looked to 60 patients, or biopsies of 60 patients IgA nephropathy, and we looked at NBL, whether NBL staining would distinguish the patients who are positive for the NBL versus the negative ones. And you see that about 15% or 25% of the patients are positive for NBL. If you go to these patients, those which are positive, positive for IG and NBL, that they have more proteinuria as compared to the one which are negative. It's interesting to note that the hematuria was reversed, and most clinicians tell me that hematuria is on the one hand, say a kind of marker for IgA nephropathy, but it's not a severity marker of disease. But looking to mesangial proliferation and extracapillary proliferation, you see that the positive cases are more severe in their histologic and progression cases. So what we see is that in IgA nephropathy, and this study has been repeated now by many others at different places, there's about 25% of the patients that are NBR positive, C4D positive. They activate the lectin pathway, and these are the more severe cases. So potentially, the deposition of C4D together with NBR is a good biomarker for the severity of the disease. And those which are negative for NBR and C4D, but they still have alternative pathway activation, are less severe. So to bring it together in IgA nephropathy, we know from the old days on that there is alternative pathway activation in most of the cases, lectin pathway activation in about 25% of the cases, and this balance determines the final outcome. We do not know at the moment whether this alternative pathway activation is dependent on the amount of activated factor D which is present in this patient. So it may be that this, let's say, the internal balance between activated factor D and pro-factor D determines the outcome of the disease. And just for your information, there are many inhibitors of complement which are being developed and which are in the pipeline. For the time being, there are actually potentially only two which are in the clinic. One is eculizumab, controlling C5-C9 activation, and the other one is C1 inhibitor. All the others are still in, say, phase 1 or phase 2, or are just in the pipeline of experimental studies. I have to mention at this point that, let's say, most of these drugs are very, very, very expensive. And at the moment, we are working on a very cheap drug, and hopefully in 2 years, we will be able to bring that here and tell you what the outcome is. But at least, for the time being, I can mention you that the drug we are developing is very active in, for instance, C3GN in mice, and also in controlling inflammation at the site of, let's say, endothelium. With this, I would like to thank my collaborators, who are many both in Leiden, in Groningen, and many other places in the world, etc. So thank you very, very much for your attention.
Thank you very much, Mo. Very stimulating talk as always. Helen has some questions.
Yeah. Can I
Please.
take the first
Yeah, you
one?
can take it.
Thank you very much for this insightful. Thank you for the compliment, and particularly the practical applications like in IgA. My question is, nephropathologists think in boxes, like we divide glomerular diseases in immune complex mediated and non-immune complex mediated. And lately, we recognize C3 glomerulopathy as well. So, however, things are not black or white, and the classic examples of non-immune complex mediated disease is minimal change in FSGS. Sometimes you see immune complexes in FSGS. Would you give us your opinion about what these mean and how the pathologist should treat these patients and communicate to the nephrologist?
Yeah, a very interesting question, because potentially control of complement activation takes place at 3 levels. 1 in the fluid phase, 2nd at the tissue level, and 3rd by the integrity of the tissue. So once you have, let's say, apoptosis, you have a flip-flop of the membrane, and that then makes this tissue a kind of complement activator. So the stage of the disease determines very much to which extent complement will be activated. So we have to think in a more dynamic fashion. In early phases of the disease, it's mostly so-called pathway dependent. So it can be activated by antibodies, it can be activated by the antigen, or it can be activated by deposited immune complexes, etc. But getting further from there, the moment you have apoptosis and injury to the tissue, all pathways contribute to further complement activation. And in the case of, for instance, at the end, I would say that it would be very, very interesting to have, let's say, divide up the patients' age brackets and look to the type of complement activation that takes place. It was not only for that disease, but for all the renal diseases, I think. Because if you go to experimental models, for instance, if you take, for example, mice or rats, if you take older mice, even though they don't have any immune complex, etc., they display complement activation. And if you look to the very young ones, they are completely free of complement. And this can have to do with the, let's say, the integrity of the tissue itself. So I think you raised a very important point, and I think we really should go back and look in more detail how, for instance, development of disease takes place, how the different age cohorts look like, etc., etc.
Okay, other questions? Boston?
Yeah, another question. First of all, thanks for this wonderful talk. It has been very interesting. Well, I perfectly agree with you that C5b to 9 has dose-dependent effects. So the small amounts lead more to an activation and large amounts more to cell lysis. However, I feel if you look at the stainings for C5b to 9, I feel a discrepancy because you have many GN forms in which C5b to 9 is deposited in very, very large amounts, but you do not see any cell lysis, and the other way around. So I feel that there could be also an effect of trapping of these terminal complexes. So maybe it could be important where exactly these complexes lie. Is that trapping in immune complexes, or is it important that they are directly at the cell surface? What do you think about it?
Yeah, look, it brings us actually to the point whether there are specific receptors or binding sites of fluid phase C5 C9. There are, as far as I know, there are only 2 publications alluding to the fact that there may be C5-TLC9, specific C5-TLC9 receptors. One is from Ann Nicholson in Boston, and the other one I forgot. And actually, and these studies have not really been repeated very often. So my feeling for the time being is that when we see C5-TLC9 somewhere, that is presumably generated locally. But at the same time, I have to mention the work of a friend of mine in Israel. And he showed that the position of C5-TLC9, let's say on nucleated cells, is changing all the time in the sense that, for instance, if you deposit C5-TLC9 on an erythrocyte, it stays there. But if you deposit it on nucleated cells, it's removed from here. So it may be that this removal changes something to the function of this molecule, this complex itself. But I'm not so very sure of that.
Any other questions? This is not the case. I had a similar question as Thorsten, because when you look at the end graphs, you rarely see, or sometimes you see the deposits right at the cells, but more frequently you see it away from the cells. And especially, I mean, you all have seen these ring-like structures on the end, and when you ask people, well, the old pathologists what this is, they all say, well, this is C3. So why, and we really stressed the importance on the local activation. So why is most of the complement we see far away from the cells?
Yeah, let's say there's continuous complement activation. So if you look to, let's say, sensitive markers for complement activations, such as, say, the inactive molecule IC3B, C3A, or C5A, then there's almost continuous complement activation. The question is, And we believe that under those conditions, there's sufficient protection of your endothelium and blood-exposed cells to this limited amount of complement activation. But, for instance, in atypical HUS, where you can have mutations of factor H, and factor H is known to be able to control complement activating fluid phase, but it also has a cell-binding motif to it. And it can bind, for instance, to endothelial cells, enhancing the potential of endothelial cells to protect themselves. What happens in atypical HUS, for instance, is that you have limited binding of factor H to the endothelium, and then this endothelium is less protected. So it's still protected, but to a lesser extent. And then you see that gradually on, you have injury to the endothelium, further complement activation, etc. And especially also in the atypical HUS, you don't see the disease at time 0 of birth. Generally, it occurs 20, 30 years later. So the question is, how long do we have to accumulate complement activation before you have, let's say, clinical expression of disease? So it may be there biologically, but we don't see it. Because it would be great if you could take biopsy so everyone can carry moment in life.
Well, there would be no kidneys left. Lots of work for the pathology. So, Eduardo, the last question.
I think thank you for your talk. Very interesting, because the C3 now is the main actor in the nephropathology. But the problem, in my opinion, is not only this C3, the deposit of the C3, as you explained it very well, but depends, in my opinion, the interrelation between C3 and endothelial cells. In my opinion, it's like hemolytic uremic syndrome, atypical or no atypical. Depends only the C3 deposition and the interaction of endothelial cells, because the endothelial cells also remove laminin, basal membrane, mesangium, etc. What is your opinion about that?
No, I agree with you in the sense that it would be great to have, let's say, a good measurement for, say, the T1/2 of endothelial cells in different people. Having said that, I mentioned that, let's say, the older you get, the more injured your endothelium potentially is because of the change of the glycolandscape, landscape, because of all the things you eat, smoke, etc., etc. So, let's say, just in aging, complement plays a major role because it actually not only complement but also innate immunity. But I exaggerate. I tell to my students, it's the endothelium is protected, but once it starts to be recognized by your innate immunity, the innate immunity carries you slowly to your death by attacking you all the time. And it's a kind of an innate autoimmunity. So it will be great in the future if we can just control this by, let's say, a limited inhibition of complement with an aspirin-like drug or something like that. So then we could stay young forever.
Well, I don't know if the amyloid fiber between the cortex somehow pulls to the nature. That's another question. So thank you very much.
So now we move on from the very old